Hey guys, this is question 4 from the chapter 9 through 10 for response questions. This is a really good question. This is a good question because it involves pretty much every concept that we've covered thus far. These are the types of questions that you got to get used to seeing because there's rarely going to be a question that involves just one concept. It's going to be a question that combines everything. So this one's got energy, this one's got rotation, this one's got forces, and it's got kinematics. All right, so let's just dive right in. Part A, we've got derive an expression for the height of the ramp h. Express your answer in terms of v initial, m, and fundamental constants. Now, since we have energy is the easiest way to do this problem. All right, so here's what we got to think about. In the context of the problem, it says that the ramp is frictionless, all right? That's important because it means that we're not going to lose any energy to thermal or any dissipative forces. So focusing in on this first section of motion, I've got energy initial up here and energy final down here. So what I can say is that at the very beginning, I've got potential energy due to gravity, and then at the very end, all of that potential energy due to gravity has been transferred into kinetic energy with no loss of energy. And then I can go about solving this. So potential energy due to gravity is mgh, kinetic energy is 1/2 mv squared. And guess what? This v is v initial because this right here is where my kinetic energy is. It's at the very end, right before it enters the ring. So v initial is what I'm solving for. Well, what's nice here is that mass is going to cancel out. So then I get, oh, sorry, I'm solving for height, not v initial, my bad. So height is going to be equal to v initial squared divided by 2g. And that's my answer. Now, you certainly could have done this. You could have done this with kinematics. However, we were just able to do this in 3 lines of work. Kinematics, it's going to be just much more of a nightmare, all right? So there are 3 points here. 1 point for recognizing the conservation of energy, 1 point for subbing in properly, and then 1 point for solving it correctly. So again, show your work, guys. Please, show your work. You're missing easy points if you don't. All right, moving on. Here is the vertical component of the net force on the block, upwards, downwards, or 0, as it moves in that ring. So the answer here is 0, and here is the reason. There's no acceleration in the z world. All right, now remember, the z world is up and down. So here the acceleration in the z world is equal to 0 because the sum of the forces in the z world is equal to 0. The only forces acting on the block while it's in there are the force of gravity and the normal force from the ground. Those two balance each other out. There's no acceleration up or down. So the vertical component of the net force must be 0 while it's in that ring. All right. The points there on this one, there were 2 points, 1 for the answer and 1 for the correct justification. Moving on. Here, so again, this one's a little bit harder than it seems. It says draw an arrow starting on the block to indicate the direction of the horizontal component of the net force on the moving block when it's at the position shown. Okay, so right now we're looking at it from the top side. What I want you to imagine is if we're looking at it from the side view. All right, so here is the side view, which means everything in my viewpoint is the horizontal direction, all right? So think of it more as a flat view. Anything that's pointing within the ring is gonna be in the horizontal direction. So what we gotta think about is that I certainly have a force in the horizontal direction here. And because I have an unbalanced force in the centripetal direction, I'm going to have a centripetal acceleration. However, I also am experiencing friction between the wall and the block. So because I'm experiencing friction between the wall and the block, I'm going to have a tangential acceleration as well. And the summation of those 2 accelerations gives me a total acceleration in this direction, which can also be rewritten as my net force, right? So I've got a force in the centripetal direction or in the radial direction, then I've got a force in the tangential direction, which means that my net force in the horizontal direction is pointed in that direction. All right, and this is because of the normal force from the wall and the frictional force. All right, both of those things work together here. Point totals on this one. This question was worth 3 total points. You had 2 for the correct direction and then 1 for the correct rationale. Now we get into more forces and kinematics here. So don't overthink these. A lot of us really did that here. So let's talk about the first one. Determine an expression for the magnitude of the normal force exerted on the block by the circular wall as a function of V. Okay, let's go back to how we set these problems up, looking at the radial, tangential, and Z direction. Here, we care about the radial direction. So if I look at like a force diagram of what's happening here, I've got force gravity down, normal force up, and then I've got another normal force in the radial direction. So here's my Z-axis, here's my radial axis. Now if I reframe this and I make this my tangential axis and this my radial axis, I still have a normal force pointed in, but I also have a force of kinetic friction in the negative tangential direction. That is going to be important for the next problem. So I'm just going to move that down there. So let's talk about what's going on here. In the radial direction, I've got the sum of the forces in the radial direction is equal to the normal force. That's the only one there. I also know that my forces in the radial direction are always going to be equal to mv squared over r. So guess what? This is the function of the magnitude of the normal force as a function of v, because guess what? I can use r and I can use m in my expression. So the normal force here is equal to mv squared over r. That's it. There was only 1 point on this because of how relatively simple that was. Now, part D, we've got 3 points built into this. So you know that it's going to be a little more complex. So again, let's look at this diagram that I've made here. And this is in the radial and tangential direction, which means that the Z direction is coming out of the page. All right, so imagine that this normal force right here is pointed out of the page in this diagram. So let's look at what's happening in the tangential direction. Some of the forces in the tangential direction, I've got a negative force of kinetic friction. That's important that it's negative because it's slowing the object down. This is equal to mass times the acceleration in the tangential direction. So let's plug some stuff in. This is going to be equal to negative mu times the normal force, which is equal to mass times acceleration in the tangential direction. Well, I have an expression for normal force, so let's plug that in. So I get that negative mu times mv squared over r is equal to m times the acceleration tangential. Well, guess what? These m's cancel out, so I get negative mu v squared over r is equal to my tangential acceleration. And that's what we got. That negative, don't forget the negative, guys, because in this problem, obviously the negative is a part of the correct answer. So you had 1 point for getting the setup correct, 1 point for making the substitution of the normal force, and then 1 point for the correct answer. So make sure that negative is there. Now the last problem. All right. We have seen problems like this twice now. You have to make a differential equation. All right. So here's what we need to realize first. That we want to derive an expression for velocity. What I want to think is that, okay, acceleration is equal to the derivative of velocity. All right? Well, when I have an expression for acceleration here, I have the tangential acceleration. So what I can say is that dv dt is equal to negative mu v squared over r. All right? 1 point right here. Okay? So there is 1 point, actually there's 2 points. There are 3 points total on this problem. 1 point for recognizing that acceleration is equal to dv dt. And then 1 point for having that negative there. See how important that negative is? Very surprising. Now, we're already at 2 out of 3 points, so where else are the points going to come from? Well, what we need to do on these problems is that I want to get all of the v's together, all right? So right here, I want to get this v with this v, and if I had any t's, I'd want to get the t's with the t's, but v is the only variable that I have. So let's rearrange and get the constants on one side and the v's on the other side. So here's what we're going to get. I'm going to get dv over v squared is equal to negative mu over r dt. I've got my v's together, I've got my constants together. Now the goal is to get an expression for velocity. So what I need to do is I need to integrate both sides. Now the question is, what are my limits of integration? Well, we want to get an expression. This word is important because it means I want variables in there. I'm not going to get a number here. I want a general expression. So I'm going to evaluate t from 0 to t because t is always going to start at 0. I'm going to evaluate velocity from v initial to v because I don't know what my v initial is. All right? Remember, this is when the object is entering this this ring here. So it has a v initial, and I don't know what that is yet, so I can't assume that it's 0. And guess what? This right here was the final point on this problem. All right, so if you did this right here, you got 3 out of 3. Now, you certainly could evaluate the integral, but here's what you need to recognize is that there's not points, there's usually like 1 point built into actually evaluating the integral. So do not waste your time simply evaluating the integral because it's really not that important. But if you did evaluate it, you'd get that v is equal to r times v initial all over r plus mu v initial times t. Or you could have gotten v is equal to v initial over 1 plus mu v initial t over r. Either one of those would have been the correct answer. Alrighty.